Hello, everyone, and today we're going to be talking about how we can determine the kinetics of a multi-step reaction. So one of the things we have to watch out for when we're dealing with multi-step reactions is that not everything happens at the same pace, which can really throw us for a bit of a loop. So the first type of system I want to examine is almost the most simple variety of system we can come up with, where I have some sort of initial reactant A, which goes to some product P. Unfortunately, there's some sort of intermediate in the middle. So I've got two elementary steps. A goes to I, and then I goes to P. Now, the unfortunate part is each one of these has its own rate. And that's going to really play havoc with how I describe the kinetics of the system. So we're going to go ahead and start by treating this system similar to our single elementary steps. So first, let's go ahead and try and determine the concentration of A. Well, lo and behold, the concentration of A is simply going to depend upon the rate of consumption of A. So it's just going to be given by negative of the rate constant for the first step times the initial concentration of A. You can go ahead and integrate this form fairly readily. And this again should hopefully make a certain degree of sense because no matter what these two rate constants are, as soon as this reaction has proceeded past this first step, it's not coming back and so won't affect the concentration of A. Now, the concentration of our end product gets a little bit messier, as the concentration of the product is going to be given by the rate constant of the second step times the concentration of our intermediate, which unfortunately means we now need an expression to describe how much of the intermediate is present in the system. So the best way to try and approach this is to try and figure out how the concentration of my intermediate is going to change with time. So we can split this into two parts. We have the intermediate forming reaction. So the concentration of the intermediate will increase based on the rate constant of the first step times the concentration of A. And I'm going to consume my intermediate based on the rate of the second step, which is again going to now be given as negative the rate constant of the second times my intermediate concentration. Now, we can simplify this system a little bit more by replacing the unknown that is the concentration of our initial reactant A with my pre-existing equation for A, which is going to depend again on the initial concentration of A and the amount of time that has passed, as well as the actual rate constant. However, that doesn't exactly simplify our system that much. And this is going to be, again, slightly problematic, as now I've got a rather messy differential equation, which is going to depend upon the change in concentration of I and temperature. Unfortunately, I is here, time is here. Yeah, I've got a little bit of a mess here. And so trying to integrate this system will be quite tricky. However, using some differential equations, we can actually reduce the integral of our concentration of our intermediate to essentially a set of prefactors, which depends upon the concentration of, depends upon my two rate constants, as well as the amount of time elapsed. So not too surprisingly, we will see a great deal of fluctuation of my intermediate concentration as time progresses. And again, the intermediate concentration will also be, not too surprisingly, dependent upon the initial concentration of A. Higher initial concentration of A, the higher the intermediate concentration I can support. Now, this gives us a set of equations for our concentration of A at any given time, the concentration of the intermediate at any given point in time. We can derive the concentration of our product essentially using conservation of mass and saying, well, all of my species has to be present, all of that A that I originally added has to at any point in time be either A, the intermediate, or my product. So we can then solve for the product and derive a rather fun and messy equation for the concentration of my product based on my two rate constants, again, in a multi-term coefficient, the amount of time that has passed, and the initial concentration that I fed into the system. And again, we still have our concentration of our reactant as well. Now you can go ahead and then plot these three expressions. And again, depending on the rate constants, you'll see slightly different behavior. But you're going to notice one of the reasons this expression is, this system is going to be kind of hard to describe. And it's worth noting that this particular graphical form has assumed a fairly fast initial rate and a relatively slow rate for the second step. So not too surprisingly, we immediately see my reactant drop, and this has built up a large supply of my intermediate, which then again slowly tails off, and then the product builds up. Now, as you may have noticed, this is a method that does work, but it quickly devolves into, well, let's be frank, a lot of rather complex differential equations. And because chemists tend to be lazy, we want to skip as much of this differential equations as we possibly can. So we need to find a way to essentially simplify the system. So one of the approaches we can take is, let's say that my intermediate is going to be relatively high energy. So in this case, what I'm going to assume is that my second step will be fairly rapid. So I have a slow initial formation of my intermediate and a rather fast consumption. So this is kind of the opposite of the graph I just showed you. Now in this case, what we're going to see is we're going to keep a relatively low concentration of my intermediate, because pretty much as soon as I form my intermediate, it's then consumed in the subsequent reaction. And what we can say is that, well, not only is my intermediate concentration going to be fairly low, it's also going to be fairly constant, because I should be seeing about as quickly as I form my intermediate, it then gets consumed to make my product. So I have a low, steady concentration in my intermediate. And this is called the steady state approximation. And this will be one of your best friends while trying to solve kinetic systems. We desperately hope that everything follows the steady state approximation, because otherwise we're in deep for a lot of really messy differential equations. So one way to mathematically represent our steady state approximation is under this assumption that the concentration of any intermediate phase is going to be zero. So after essentially an initial induction period where I've generated a little bit of I, then the concentration of I should stay relatively steady. So when we're able to apply this approximation, well, this means that if the change in the concentration of I isn't, changing, then what I can do is simplify that expression we just generated and say that, hey, guess what? The rate of production of I, K1 times my initial concentration of A, has to equal my rate of consumption of I, which is this rate of the second state, the rate constant for the second step times I. And again, this gives us the concentration of our intermediate times the ratio of my two rate constants times the concentration of A, which we can then use to determine the rate of production of my product species, because this will be dictated by K2 times the consumption of I. But when we then insert our expression for the intermediate, it just gives us an expression times the rate constant of the first step times my initial concentration of A. Now, what this really does is it really illustrates that in this process, again, assuming that the rate constant for the second step is much greater than for the first step, congratulations, the first step is called rate limiting. And you can see this because the rate is entirely dictated by this, the rate constant, a rate of production of the intermediate, and thus the rate constant for that first step. Now, another good way to try and look at the steady state approximation is through analogy. So this was first brought up to me while I was sitting at a chemistry conference listening to lectures on steady state. Well, this being a chemistry conference and everybody in attendance being grad students, everybody was copiously taking from the free coffee. So we were rapidly taking up a lot of coffee. And after essentially an initial induction period of the first set of lectures, where everybody had been loaded up and primed by the first step of making coffee, we were then stuck on that second rate limiting step, which was the slower process of needing to relieve oneself from said coffee. And so, not too surprisingly, after about 45 minutes into the conference every day, we've hit our induction period and we reached what I like to call steady state coffee. And it's much the same when we're dealing with a lot of these simple reaction mechanisms. There's often a slow induction period where you have to prime the system, generate that primed intermediate of grad students with coffee before you can essentially generate product. However, we can also use this steady state approximation to describe slightly more complicated systems. One of the more common ones is what's called pre-equilibrium. So now we're going to be assuming the second step is going to be fairly slow. And as you can imagine, if the second step of an intermediate decomposing to product is fairly slow, it wouldn't be unheard of for this first step, in this case, A plus B going to form intermediate, is actually going to see some extent of back reaction. So I'm going to have my intermediate in this case not only forming product, but also decomposing to form my reform my reactants. So we can describe the system in a fairly similar set of approaches. So we're going to be able to describe the formation of our product again based on the rate constant for the second step times the concentration of the intermediate. Now what we can do is describe the concentration of my intermediate in order to generate the rate of production of my product. And we're going to do this using the steady state approximation. We're going to assume in this case that the second step is fairly low, but that as soon as an intermediate molecule is formed, it's either used to generate a product or to reform my reactant, keeping this concentration relatively steady. So we've got one mechanism to generate my intermediate, and that's essentially the combination of my reactants A and B. So the rate for that production is going to be given by the rate constant for this first forward step times the concentration of each of my reactants. But I have two different ways for my intermediate to decompose. It can either decompose to regenerate my reactants, which is going to be given by the intermediate concentration times the rate constant for the reverse reaction, or it can decompose to generate my product, which is going to be given by the concentration of the intermediate times the rate constant for the forward reaction. Now, since all of this change has to equal 0, what it does is it lets me isolate all of the terms in which the intermediate is involved. And I can then go ahead and combine these two rate constants. So what we find is the concentration for I times the sum of my two rate constants, so the two different ways I can decompose, is equal to the concentration of my two reactants times the rate constant for the formation. Now we can then try and apply this to the production or the generation of my product species, which again is going to be given by the rate constant for the second step times the concentration in the intermediate, which we can then insert into this equation. And then we can do some quick but very slight rearrangements. I'm going to essentially pull out the concentrations of my reactants A and B. And this leaves me with essentially one big combined rate constant. So one of the things that's worth noting is when you do measure rates of reaction, oftentimes you aren't measuring individual rate constants, but instead something like this, where it's a combined rate constant of several elementary steps, something to kind of be aware of. But one of the things I want to do is kind of illustrate several different scenarios that we can apply to this reaction. So one of the big cases that we are often interested in is what happens if we have a slow reverse step. So essentially, once I form my intermediate, I'm more likely to proceed to product than back to reactant. So in this case, K1 will be fairly large, K2 will be fairly intermediate, and K1 prime will be fairly low. Now, in this case, what we see is that K1 is much smaller than K2. So I'm going to be able to reduce my rate constants to K1 times K2 over K2. Well, this is going to just be the same thing as K1. Well, really what this did is it showed me that this whole process, in order to maintain steady state, the first step is going to be the relatively kinetically limiting step. Because as soon as I form intermediate, if it has to decompose, it's going to tend to decompose to the product because it's too slow to decompose to the reactant. In reality, if K1 is also much larger than K2, you may have to actually apply a non-steady state system and keep your fingers crossed. But again, what this generally produces is the same thing we saw from sequential reactions. Because if K1 prime is fairly low, it may as well not be involved at all. And again, this is what we saw with our initial case of A goes to I goes to P. We'd see something very similar, but now we have A and B both involved. So let's go ahead and try and look at another limiting case. This is one we call pre-equilibrium, where we're going to assume that K2 in this case is fairly low, and the reverse reaction is fairly facile. So I form I, and then I tend to reform my reactants. And then I form I, and then I tend to reform my reactants. Then I form I, then I tend to reform my reactants. Then I form I, and eventually I make my product. So in this case, what we're going to find that if K2 is much smaller than the reverse reaction, then I can essentially drop it from the summation term. And I'm reduced to K, the rate constant for the first forward reaction times the second forward reaction divided by the reverse reaction. So what this shows is what we call a pre-equilibrated state, where I constantly have my intermediate forming and decomposing with my reactants, and then only ever so occasionally producing the product. At which point it's very clear that K2, the second step, is clearly rate limiting. But the nature of the equilibrium will drastically change how much intermediate I'm feeding into the second step of reaction. So not too surprisingly, if this reverse reaction is very facile, I'm not going to have much intermediate to drive the reaction forward. If this reverse reaction is fairly low, then I will see a much greater generation of the intermediate and thus formation of the product. Now, one of the other things we can do is say, well, let's see how this compares to another scenario, which is if the second step is rate limiting, well, isn't that kind of like talking about this first step being in equilibrium? So in this case, I can try and treat this first system using the equilibrium constant, which we showed previously to be the same as the ratio of the forward over the reverse rate constants. So again, this is just the equilibrium constant for this first step of the reaction, which again, we know that the equilibrium constant is going to be of the form of products, in this case, the intermediate, over reactants. Well, I can then go ahead and rearrange this. And what we get is, again, the concentration of the intermediate times the ratio of my rate constants times the reactant, the concentration of my reactants, which I can then insert into my rate equation for the second step. And at which point, congratulations, we just reproduce the same kinetic behavior as the steady state approximation under the assumption that the second step was rate limiting. So this gives us another way to talk about uh, the kinetics of a system. We're going to generally try and hope that all of our intermediates are going to function under steady state, and this will be a fairly good approximation. However, if you're given information that one step is in pre-equilibrium, uh, one step is rate limiting, this means that we can tend to treat all of the previous steps as being in equilibrium and replace uh, the behavior of the intermediate using a rate constant. And this can, or a equilibrium constant. And this can be a very good way to try and treat a system. So next time, we're going to be trying to take a lot of these same lessons of steady state and applying it to a specific case, starting with good old enzymatic behavior. Here we come, Michaelis Menten. Till then, take care.